Alright, hi everyone. So we'll start the lesson by doing a quick recap on all the content that we learned in the topic 9, complex numbers. Okay, so the first lesson, we tried to talk about what is the real number system and why is that. So you have an imaginary number and also the complex number. So a simple definition that given by a new symbol that is introduced to you guys is I. So I square is equal to -1. So what I stands for is square root of -1. Okay, so when we try to talk about the complex number, we talk about a form of z equal to x plus iy, okay, where x is called as the real part, then iy part is called as the imaginary part, okay. So you must bear in mind that your x and y must be in the real value lah. All right, because yeah, if let's say x is not a real value, it's an imaginary value, then it's going to make this not a real part anymore. So if y is not real, then it's going to be I times I is going to give you a real value for the imaginary part. Okay, so after that, we also learn what a conjugate is. So the conjugate of a complex number for z will be denoted as z star. So it will be given as x minus iy. Okay, then after that we learn like few arithmetic operation for complex number. So like for example, the addition, the subtraction, the multiplication, and also the division. Okay, I'm sorry, arithmetic operation. Okay, so we will try to denote everything here by using, if let's say z1 is a plus bi, and also if z2 is c plus di. Okay, so if we try to plus two complex number together, so it means that we will try to plus the real part together, so which a plus d, then after that b is going to plus d for the imaginary part. Okay, so if we are going to minus one complex number, then it will be the real part minus the real part, so a minus c, and then plus the b minus d. All right, then for the multiplication, so when we try to put together z1 multiplied with z2, so you will actually you will just expand it as normal, like how you normally expand a polynomial equation. So like a times c, it will give you ac, then a times di, so it will give you a di. So bi times c, so plus bci, and then plus bdi square. So I square is -1, so that's why when we try to rewrite it again, we can write AC minus BD plus, then for the imaginary part, we have AD plus BC. Okay, so that's the part for multiply. So for division, normally when after we try to write the division, so for example, a plus bi over c plus di, we will not leave our answer to have complex number in the denominator. So we need to rationalize it by multiply with a fraction that consisted of the conjugate. Okay, so in this case, it will be multiply with c minus di and c minus di. All right, so after we expand it, so a plus bi multiplied with c plus di is going to be exactly the same thing like what we have done for the multiplication just now. Okay, then after that, for the denominator part is going to be, so you can imagine that the CDI and CDI, they will cancel off each other. So what do you left? You left with c square, and then the di multiply di, negative di, you have negative d square I square. So I square will give you -1, so that's why it will make your negative d square become positive. So plus d square. Okay, so by doing this, then you will not have any complex number in your denominator anymore. Okay, so that's the idea. Okay, then after that, in the second lesson, we talk about the modulus and also the argument for a complex number. So the modulus of a complex number will be denoted as modulus z. So this is also meaning what is the length of the complex number if you try to place it in a Cartesian plan, right? So it will be equal to the modulus of z squared plus y squared. It's the same thing like when we talk about the modulus of a vector. Okay, so if let's say we are finding the argument, so argument is the angle between the positive real axis and the vector of the complex number that we have. So first thing that you must remember that you need to do is to draw a diagram. So after you draw the diagram, then normally we'll use the approach of tangent theta will be equal to y over x to solve the angle. So it's either that it's just nice that you can solve theta by using this equation, or sometimes you'll need to do pi minus, or for you to do the negative part, then you will need to do another way lah. So normally the principal argument, we will try to let our answer to be in between negative pi to pi. Okay, so that's the principle. Okay, so after that, we also know that if let's say we have a if we have two complex number that multiply each other, so for example, z1, z2, so to find the modulus of z1, z2, it will be equal to when we try to use the modulus of z1 multiplied by the modulus of z2. So if let's say we have z1, z2 and we want to find the argument, so which means we will try to plus the argument together. So argument for z1 will plus for argument for z2. So if it's divide, so it's going to be the same thing as well. So z1 over z2. Okay, so it will be modulus of z1 divided by modulus of z2. So for the argument part, so for multiplication is is plus, so that's why for divide is going to be minus. Okay, so if you have forgotten anything, then please make sure that you check back your previous notes. Okay, so when we know how to find the modulus and argument form, right, then we learn what is that meant by the polar form. Okay, so the form of the real imaginary form, which mean like z equals to z equals to x plus iy is the real imaginary form or the Cartesian form. Okay, so which means you can use an eigen diagram, then after that your x is basically the real part, then the y is imaginary part. Okay, so polar form will use a polar coordinate that consists of both modulus and argument. Okay, so there are two forms that we learn under polar form. The first one is called as the modulus argument form. Okay, so the general form for the equation is given in a form of z equal to r, then cos theta minus I sine theta. So the r here basically is our modulus, then the theta here is our argument. So the second form that we have is the exponential form. So it can be written in the form of z will be equal to r e to the power of I theta. Okay, so same thing, r is the modulus and theta is the argument. Okay, so we also know that how do you actually change between the Cartesian form, the polar form, and also the exponential form. So make sure you know how to do all that. Okay, then after that, in the third lesson, we learn about how to find the roots of the equation. So we are talking about all the equation with real coefficient. Okay, roots of equation with real coefficient. So real coefficient, which means that in your equation itself, you cannot have any imaginary term lah. Yeah, you cannot contain any complex number or imaginary number. So we know that for the first one that we learn is the quadratic equation. Okay, so under quadratic equation, there are two types of root. The first one is either you can have like two real roots, okay, or the second one is you can have two complex root. Okay, and the complex root must be in conjugate, which will give you like x plus minus iy. Okay, so for the first one is x plus iy, second one is x minus iy, which is its conjugate. Then after that, for second one, we have the cubic equation. So cubic equation meaning a degree of 3. So we have two situations as well. The first one is either we can have 3 real. This is what we learned in chapter 1. After that, the second one is we can have 1 real and also 2 complex. Okay, so remember that you would not have like 1 real and you would not have like 2 real and 1 complex, because that will give you a equation that with a imaginary part. Okay, and the complex must be in pair as well. Then the last one, we have a quadratic equation, which is of a degree of 4. So for a quadratic equation, then you have three different kind of scenario here. The first one is either you will have four of your roots are real. Then after that, you can have two real and two complex. Okay, so the two complex will be in a pair of x, the conjugate pair as well, so x plus minus iy. Okay, so the last one is you can have all the four roots are complex. Okay, so in this case, then perhaps you will have one pair, then after that the other pair, then maybe you try to put a plus bi here. Okay, so that is what we learned. So yeah, then after that we also learn how to find the square root, right? So remember, like, how do you find the square root? So you try to denote it like z square will be equal to what? Then after that you find it. Then after that, don't forget also your cube root. Okay, so yeah, this is just by solving just by comparing then solving your equation. So for today's lesson, we are going to talk about the loci for the complex number, and that's the end for this chapter and also this semester. All right, so let's start the lesson today. Hi everyone, welcome to the fourth lesson for topic 9, complex number. This is the last lesson for this topic and also the last lesson for the whole syllabus for Pure Maths 3. So after today's lesson, please spend some time to finish your homework. Then after you submit, then you can take a time to enjoy your break, take a good rest before we resume our lecture in January. Okay, so yeah, let's start by looking at the learning outcome today. So for today's session, we are going to focus on one thing only, which is to illustrate simple equation and inequality that involve a complex number by means of loci in an Argand diagram. Okay, so loci is just like a plural noun for locus. So I believe that you heard of this word before, and you know how to describe a locus in a coordinate geometry approach. Okay, so today we are going to look at how do we illustrate it if, let's say, it's given in the form of complex number. So there are these three cases that we'll be looking at today. So we will be going through together one by one. All right, so let's start with the introduction. Okay, so the first thing is we'll be looking at what a locus is. So a locus is a path that traces out by a point when the point tries to follow a particular rule. Okay, so which means that you will be given some information that tell you that what is the rule that the point must follow. Then after that, by using the rule, right, it will actually form a path that where your general point is. So the path is called as the locus. So normally the rule will be expressed in the form of either in equation, so which means that you'll be given like something equal to something, or it will be given in the form of inequality, so which means like bigger than, smaller than, or bigger than, smaller than, and equal to. Okay, so that's the idea. Okay, so now we'll be looking at the first case here. So let's look at the case 1 here. So this is the general form that represented by case 1, which is in modulus z minus z1 equals to r. Okay, so z is basically the general point that we have as in the definition of locus just now. So this is the general point that will be following the particular rule. Okay, so z will be a complex number, which means if let's say we try to represent it in an Argand diagram, then it will be a coordinate of x and y. So z1 is a non-complex number, so which means that it will be represented by one coordinate in the Argand diagram as well. Okay, then r, it will be a real constant. Okay, so let's try to look at this diagram here. So you can see that this is what we have for the general point. So this is like denoted as the z here. So you can imagine if we try to talk about this in terms of vector, right? So this is going to be the vector of z, correct? So which is like the position vector for OZ. So this can be represented by the vector z. So if let's say we try to connect here to here, then this will be the z1, meaning the position vector for z1. So how can we find the vector for this sign? So it's going to be negative z1 and then plus z, correct? So negative z1 then plus z. So when we try to rearrange it again, so this is how we get z minus z1. So this line is represented by z minus z1. Okay, now we try to put z minus z1 inside a modulus. So it will become the modulus, the magnitude or the length of this line, correct? Okay, so now try to think of it like this. So the modulus of this line, right, it must be always equals to r. So what do you think that will be a locus of z that you can put so that the distance from z1 is always equals to r? So it's going to be a circle. Okay, so let me try to erase this. So which means that you can imagine that this is my general point of z, right? So to make sure that the distance between the distance of my r here is always equals to r, I must actually follow the rule that the z must be on this circle. So no matter where is my z, as long as it's in this circle, it will 100% give me the same length as r, right? So that's the idea. So that's why for the first case, modulus z minus z1 equals to r is actually a circle. Okay, so we can try to write down the conclusion here. So which means that if z minus z1 equal to r, then z, meaning the general point, will be always lies on a circle with the center of z1, so meaning the known point, and after that a radius of r. Okay, so I hope that you can get the idea. For the first one, I think it's pretty easy. Yeah, so the idea is what is the path that the general point should be following if let's say the modulus of z minus z1 must be always equals to r. Okay, so that's why it will be a circle in this case. Okay, so if let's say modulus of z minus z1 is smaller than r, so which means your general point can lies anywhere inside a circle. Okay, so which means if less than r. So if z1 minus if z minus z1 is greater than, I'm sorry, this should be greater than, okay, then z can lies anywhere outside the circle. Okay, so that's the idea, but normally we don't really talk about the outside one. Normally we will use the inside one rather than outside. Okay, so now I'll try to explain this thing like an extra knowledge for you to realize that actually it's a circle. Okay, so you see this is the form that complex number that we have, right? So z minus z1 equal to r. So we say that z is like the general point. So maybe in here, then we try to denote it as like z plus yi. Okay. Then after that minus. So z1 is the known point that we know. So maybe we try to denote it as a plus bi. Okay. So in modulus equals to r. So when you try to rearrange it, then we will have z minus a and then plus y minus bi, correct? So how do we find the modulus for this form? So which means that we will try to do x minus a square and then after that plus y minus b square, right? Then equal to r. Okay, so as you can see, right, when we try to solve this and we try to bring this square root over the other side, what we have x minus a square plus y minus b squared equals to r squared. So do you find this equation like very familiar? Yeah, so this is actually the equation of a circle. So from this equation, then we know that this circle has a center at A and B, correct? Then after that, it has a radius of r. So this actually proves to you that the locus as is in this form is going to be an equation of circle. Okay, so that's the idea. All right, so let's look at few example for the first case. Okay, example one, on separate Argand diagrams, sketch this loci. Okay, so I'm sorry that as you can see, I actually straight away show the circle here because I realized that it's not it's not like very efficient. If I were to draw it together in this video, it will take me a lot of time to edit it, and also if I use freehand, then it will be kind of like ugly. So that's why I think that it's good that I try to draw it beforehand, then we try to discuss together. Okay, so yeah, for this picture, then you might want to put in like this is the imaginary Z, then this is the real Z. Okay, so I didn't put the label here, then perhaps you will need to add in by yourself. Okay, so A, by looking at here, then you know that is modulus Z equals to 5. Okay, so let's recall the first case that we have is Z minus Z1, okay, equals to R, right? So we have the center is equal to the Z1, then after that the radius of the circle is going to be R. So that's why for a locus that represented by modulus Z equals to 5, what is the locus going to look like? It's going to look like a circle with a center of 0, 0, okay? Because this is going to be Z minus 0, right? So that's why 0 plus 0, I. So the center is 0, 0, which is the origin, and also the radius is equals to 5. Okay, so that's why we have this circle, which is with the center of 0 and the radius of 5. Okay, so you must remember that for this locus, right, because it's equals to 5, so that's why the locus is only the circle. Okay, so you might try to write down for the first time. So which means the locus involve only the circle. So it is the points inside the circle is not included. So which means that because you want the radius to be exactly the modulus for Z is exactly to be 5, right? So that's why you cannot accept anything that is less than 5. So that's why equals to 5, it means that the general point will be located on the circle only. Okay, so we use a solid line because just represent that the circle is the answer. Okay, then after that, let's look at B. So we can see that this is going to be modulus Z lesser than 3. So by looking at this, then you also know that this is going to be a circle, then with the center of 0, 0 as well. But then our radius here is going to be 3. Okay, but this is less than 3. So which means that we do not want any point that on the circle, we only want the points within the circle. So you can see that I try to shade the region inside. So any general point inside this locus, it will give me an R that is less than 3. So I cannot locate the general point on the circle itself because that will give me like equals to 3 already, but I want it to be less than 3. Okay, so only the points within the circle, and that's the reason that why we are using a dotted line rather than a solid line, because the circle itself is not included. Okay, so like the circumference of the circle is not included in this inequality. Okay, so I hope that you can get the idea. All right, then after that for C, so this is modulus Z lesser than 4. Yeah, so that's why it will give us a circle also with a center 0, 0, and the radius is 4. Okay, so as you can see, this is less than and equal to 4. So that's why you have a similar picture like B, but then we are using a solid line because you can accept it to be on the circle as well. Okay, so that's why for this case, you can see that the region is shaded, but it's going to be all points within the circle and also within the circle and on the circumference. Okay, so that's the idea. All right, so now we'll be looking at D. Okay, so for D onwards, it's going to be not the center at the origin anymore. It's going to be at somewhere else. So let's try to look at D. Yeah, so you can see that modulus Z minus 2 minus 4i equals to 3. Okay, so by comparing with the form that we have here, right, we need to have like minus than the whole complex number. So that's why before we try to identify the circle, we must make sure that it's in the form of z minus. So as we try to put our complex number in a bracket, so what happens is it will become 2 plus 4i, right? Okay, so by having this, then only we can identify that is z minus z1 equals to r. So that's why it's going to be a circle as well. But now your center is going to be 2, 4, and the radius is 3. Okay, so this is equals to 3. So you know that the point for the locus will be on the circumference only. So it's not the points within the circle. Okay, so it's a solid line because it means that it's the circumference lah. So the points only the circumference. Okay, so that's the idea. I think you can try to write it. Yeah. All right. So yeah, the idea is for you to know how the locus look like. Then after that, you understand why is the locus included. So this is 2, 4. So that's why your center is right here. Okay. So have a radius of 3. So then you can try to draw a circle there. Okay. Then after that, number E. Okay. So you have modulus E minus 3i equals to 4. Okay, so the same thing here. So what we have here is z minus z1 already, right? So we can straight away identify. So this is z minus z1 equals to r also. So it will give us a locus of circle. So the center, it will be at, yeah, what is the, so you can see there's no real part here, right? So the real part is going to be 0. Okay? So minus 3i, so that's why the y here, meaning the imaginary part here, it will be 3. Okay, so radius of 4. So same thing, so we have a center of 0, 3, so it's going to be like 0, then after that 3. So you have a radius of 4, so 1, 2, 3, 4, and then 1, 2, 3, 4. Okay, so then you can draw a circle. So why is this? So because it's given that it's lesser than 4, right? So that's why the region that we want is only within the circle. So we try to put a dotted line so to indicate that we don't want the point on the circumference. So it's only the point within the circle. Okay, so the circumference is not included. So that's the idea. Okay, so let's try to look at the last one for the F. Okay, so for F, then you have modulus Z plus 5 lesser or equal to 2. So as Y, then we might need to change it to Z, then minus negative 5, right? Then lesser than 2. Okay, so by having this, then now we can try to, we can identify that it's a locus of circle as well. So the center will be at negative 5 and 0. So the radius is going to be 2. So that's why we have negative 5 and 0 as the radius. Then you can try to draw a radius of 2 for the circle. So this is lesser or equal to. So that's why it will be all points within the circle and also on the circumference. Okay, within the circle. Yeah, so this is like your explanation for yourself so you understand why is that so in future and on circumference. Okay, so let's move on to the next question in example 2. Okay, number 2, the points in an Argand diagram representing 2 plus 5i and negative 6 plus I are the ends of a diameter of a circle. Find the equation of the circle giving your answer in the form of z plus a plus bi equals to k. So this is the form of a locus of a circle, right? So it means that there are two information that we need for us to write the equation. So which is to get the center and also to get the radius. All right. So the information given in this question tells us that we have a circle. Then after that, we have this, let's say this is the diameter. So these 2 points here represent the end of the diameter. So which means for us to find the center, then we might need to find the midpoint of these 2 points. Then after that, for us to find the radius, then we need to find what is the length of what is the length of this diameter, then divide by 2, then we can get the radius. So that's like the whole idea. Okay, so let's start with finding the center first. So the center will be equal to, so for us to get the x, then it will be 2 plus negative 6 and then divide by 2. Okay, then after that plus the I part is going to be 5 plus I, then divide by 2. So this is the I. Alright, so after we solve it, then we'll be able to get negative 2 and then plus 3I. So this is the center. Then after that, to find the radius, we'll be using the idea of how we normally find the length between 2 points in coordinate geometry. So 1 over 2, so the length between the 2 points here, yeah, we'll be using x2 minus x1 squared, and after that y2 minus y1 squared, right? So same thing here, so we have 2 and negative 6. So 2 minus negative 6 squared, and then after that plus 5 minus 1 square. So what we have here is 1 over 2, then after that 8 square plus 4 square, which will give us 64 plus 16, which is 80. Okay, so by solving this, then we'll be able to get 2 then square root 5. So this is the radius. So when we try to write in the equation, so which means that we'll always do z minus z1, which is our center. Okay, then after that equal to the radius, so 2 square root 5. So let's try to make this in the form of z plus a plus bi. So we have z plus 2 minus 3I in modulus, then equal to 2 square root 5. Alright, so that's the idea. Okay, so let's look at next example. Okay, number 3, sketch an eigen diagram and shade the region whose point represented by the complex number z which satisfy both of these inequality. Okay, so same thing, we might need to explain our locus here. So modulus z minus 2 plus 3I modulus less than or equal to 2. Okay, so which means this will create a circle as well with the center of 2 plus 3I. Okay, then after that we have the radius equal to 2. So this is the center that we have, so 2 3, so which is here. So when we try to draw it, then it will be within this region, so it is like inside and also on the circumference. Okay, so z lies inside or on the circumference. Okay, I just write the circumference of circle. Okay, then after that, let's try to check out the next one. So we have modulus z minus 4 greater than 3. So this one is going to be a circle as well. Then the center here is 4, 0, okay, with a radius of 3. So that's why 4, 0 is here. So the radius of 3. Alright, so this is greater than 3, so which means that the region we have is outside. Okay, so that's why z lies outside. So I try to shade the pink color because like the pink color is not the one that we want. Okay, so lies outside the circle. So which means which is the region that satisfies both is actually here than outside, right? So that's why this will be the shaded region. Okay, so that's the idea. Alright, so let's move on. Yeah, but in your picture, I guess that for you, you no need to really actually shade the what inside, because I'm just showing you that this is the idea that we have, that is anything that is outside and is not on the circumference itself. So lies outside the circle, then after that, the intersection part will be here lah. Okay, so let's try to look at the case 2. Alright, so let's look at case 2. So the general form for case 2 is given in a form that modulus of z minus z1 is equal to the modulus of z minus z2. Okay, so similar to case 1, that z is a general point that will be following a particular rule. So in this case, then z1, z2 are the known complex number. Okay, so let's try to look at this diagram. So you can see that we know where is the location of z1, z2. So z will be following a particular rule that the modulus, which means the length between z and z1, must be equal to the length of z and z2. Okay, so that's the idea. So that's why to fulfill the rule here, so which means that the locus of z, the general point, must be in the middle between these 2 points. So this will create a pace which is the perpendicular bisector between these 2 points. So you can imagine that no matter where is my z, right? So as long as it's located on this locus, it will give me the same distance when I try to connect z to z1 and z2. Okay, so that's the idea. So that's why if we have the modulus of z minus z1 is equal to the modulus of z minus z2, then z will lies on the perpendicular bisector, okay, of the line joining our z1 and z2. Okay, so I think this is quite direct. Yeah, so same thing we will have if let's say is in the form of inequality, right? So if let's say that it's given that modulus for z minus z1 is lesser than the modulus of z minus z2, that it means that your z is going to be nearer to z1 compared to z2 lah, because the distance between z and z2 is greater than the distance between z and z1. So that's why your z must be nearer to z1 instead of z2. Okay, so that's the idea. All right, so now let's try to look at 2 examples for case 2. All right, number 4, on an eigen diagram, sketch the locus of z minus 4 plus I equal to the modulus of z plus 5i. Okay, then find the Cartesian equation of this locus. Okay, so now we'll try to look at this first. So you remember just now the form, so it must be in z minus z1 equals to z minus z2. So the locus here, we might need to rewrite it. So z minus, so it will become 4 minus 1 in bracket. So this will be our z1. Then after that, we will have the other point, which is z minus negative 5i. Okay, so by having these two, then we know that our z1, which means the first point is going to be 4 minus I, then our z2 is going to be negative 5i, right? So it's going to be 0 minus 5i. Okay, so by having this, then now we can try to draw the point. So we have z1 is 4 minus I, so that's why it's 4, then negative 1, so that's why it's at this point. So 0, negative 5, then it's going to be at this coordinate. Okay, so after we find this, then we might need to find out what is our midpoint so that you can draw the perpendicular bisector, right? So the midpoint for z1 and z2, okay, so it's going to be 4 plus 0 divided by 2, and then plus, then we have negative 1 plus minus 5, so minus 5 divided by 2i. Okay, so we can get our answer 2 plus negative 3i. Alright, so by having this, then we know that our midpoint is at 2, negative 3. So that's why it's at this point. So now we will need to draw a line that pass through this line joining Z1 and Z2 with a perpendicular angle. So which means that it's going to be like 90 degrees. Okay, so this is the line that we have. So normally, right, when we try to joining these two known point together, we'll try to use dotted line because to indicate that that is the line that we use as our reference. Then the real answer for the locus, then we'll use the full line. Okay, so that's the idea. Okay, so after we sketch, then the question wants us to find the Cartesian equation of this locus. So same thing, since we have midpoint already, so now we might need to find the gradient. So the gradient for PQ, it will be equal to, so same thing by using here. So we have negative 1 minus negative 5 then 4 minus 0. Okay, so we have negative 1 plus 5, so it will give us 1. So which means that the gradient for the perpendicular bisector, yeah, I'm just writing a short form, perpendicular bisector will be equal to negative 1, okay, because they are perpendicular to each other. So m1, m2 should be equals to negative 1. So after we found this, then we can find our equation. So y minus, so we have our y here, right? So y minus negative 3, and then equal to the gradient, then x minus 2. All right, so by having this, then we can form our equation. So y will be equal to negative x, so plus 2 and minus 3, so that's y minus 1. So this will be our equation. So you can try to check. So this one should have a gradient for negative 1. So that's why you can try to see that it's like one box and 1. So when x move for 1 unit, then your y also move for 1 unit, and the direction is in a negative direction, then your y-intercept is negative 1. So that's why it's correct. Okay, so that's the idea for example 4. Okay, so let's try to look at next one. Okay, number 5a, sketch on the Argand diagram the loci given by these two equations. Then after that, show that the loci actually intersect at the point of negative 2, negative 2i. Okay, so let's try to start with the sketching first. So we have the first equation is given by modulus of z minus z plus 2i will be equal to 5. Okay, so this is the form of z minus z1 equals to r. So this locus is a circle which with the center of 1 plus 2i. Then after that, the radius of 5. Okay, then after that, for the next one, then we might need to rewrite it in the form of z minus z1. So z minus 5 minus I, so this will become our z1, then equal to z minus, then minus 3 plus 5i. Okay, so every time remember before you actually identify the point, right? So make sure that it's always in like a bracket that tell you what is Z1 and Z2. Okay, so by having this, then we know that we have the 2 point. So Z will be a perpendicular bisector, right? So Z lies on the perpendicular bisector. So I'm just going to write PB lah. Okay, perpendicular bisector of line joining the 2 point, which is 5 minus I and negative 3 plus 5i. Okay, so now we can try to sketch it. Yeah, so for the first one, the circle, so we have 1 and 2, right? So that's why 1 and 2 is here. Okay, so this is the center for the circle. Then you are going to draw a radius of 5. So 1, 2, 3, 4, 5, then draw a circle. Okay. Okay, so for the second locus, we have the point of 5 minus 1, so it's here. Then after that, negative 3 plus 5i, so it's here. So the dotted line is the reference line that joining these 2 points together. So the locus is the perpendicular bisector. So you might need to find out the midpoint so that you can draw the perpendicular bisector, right? So the midpoint will be equal to x1 plus x2. So we can use negative 3 and then plus 5 over 2 and then plus, so the y1, so 5 plus negative 1 divided by 2. Okay, so I. So we have 2 over 2, so it gives us 1, then 4 over 2, it gives us 2. Okay, so the midpoint will be at the point of 1 and 2 lah. Then you can draw a perpendicular bisector. Alright, so after you got this, then now we move on to part B. Okay, so this is the, yeah, so make sure every time when you have this, try to write down, yeah, because I'm like putting it in the, I can't draw the arrow with what I have here, so that's why. So make sure that you do the complete one in your questions. Okay, then after that, let's try to look at B. So show that this loci will intersect at the point of negative 2, negative 2i. Okay, so by looking at this, then definitely because this one I use like a proper circle, then I find out how is the 90-degree look like, then I try to draw the line. So you can see that the two locus actually intersect at -2, -2i. But if let's say we are using sketching, right? So you'll realize that I may not actually get this exact point in my diagram. So that's why, how do I actually check it? I need to make sure that if let's say this point can sorry, if let's say the locus intersect at this point, which means that this point will be able to satisfy, will be able to fit well into the two locus equation that we have. Okay, so which means that we might need to check one by one that the left hand side is equal to the right hand side. Okay, so the idea is if they intersect at this point, then that means that point must satisfy both equations. It's the same thing like when you do a simultaneous linear equation to get the intersection point lah. Okay, so for B, so which means that the point that we are checking now is z equal to -2, -2i. Okay, so now let's try to check for the first locus first. So z minus 1 plus 2i modulus. Okay, so substitute the z with -2 and -2i. So you need to do it step by step so people can see that you are actually proving it. So -2 minus 1, you have -3. Then after that, -2 minus, so -4i. So when we find the modulus of this, so we will try to use Pythagoras theorem. So 3 square plus 4 square. So square root of 25. So that's why it's equal to 5. Okay, so by having this, then we know that it's satisfied because the first locus tells us that z minus z1 is equal to 5, right? So based on the locus. Okay, so the same thing for the second one, we need to fit into both left hand side and right hand side. Okay, so now for the left hand side, we have z minus 5 plus I. So same thing, substitute. So -2, -2i minus 5 plus I. Sorry, I might need to write smaller here. So -4i, so -7, then after that plus, so -i. Okay, so same thing, put in modulus. So we have 7 square plus 1 square, which will give us 50. Okay, then after that, same thing, check for the right hand side. So z plus 3 minus 5i. So same thing, substitute. So -2 minus 2i plus 3 minus 5i. So now we try to put in. So we have -7i. So we realize that when we try to find the modulus, same thing, it will give us the modulus of 1 square plus 7 square, right? So here I will have square root 50 as well. So that's why I know that the z minus 5 plus I equal to z minus 3 minus 5i. Okay, so by having this, then I know that this point satisfied for both equation. So the two locus will intersect at the point of -2, -2i. Okay, so you can just write down the conclusion there. Alright, so you can write that since z equal to -2, -2i satisfy both locus equation, so the two locus intersect at the point of -2, -2i. Alright, so just like that. So now let's try to look at the last case. Alright, so case 3. So the general form here is given that argument for z minus z1 is equal to theta. So same thing, so z is the general point that following the rule, then z1 is a known complex number, then theta is the angle lah. So which means like normally how we find the argument. So when we try to look at this diagram, so this line can be represented by the vector of z minus z1. So for this z minus z1 to have an argument of theta, which means that you will have a direction of positive axis. So the argument, the theta, will be the angle between the positive real axis and the vector that you have, right? So that's why this locus of z is a half line. So why is it called as a half line? Because as long as my z is going to be located on this line, no matter where is the line, right, it will produce me the theta when I try to find out what is the angle between my vector and also the positive real axis here. Okay, so sometimes it's called as a half line or sometimes it's called as a part line. So the idea is that it will be a line that start from z1 and have an argument of theta, but the length can be infinite. So as long as it's located on this line, so it will give me that argument for z minus z1 is equal to theta. Okay, so just like that. So now same thing, let's try to write down the conclusion here. So which means that we have if, okay, our argument for z minus z1 is equal to theta. So which means that the locus of z is a half line. Okay, so the half line will start at the known point that we have. So starting at z1. So how do we draw the line? So we'll be following the angle theta that is given. So at an angle theta with the direction of positive real axis. Okay, so same thing. Now let's try to look at another 3 example before we end the lesson today. Okay, so let's try to look at example 6. Okay, example 6. So on a single argument diagram, sketch the loci for modulus z equals to 4 and argument of z plus 2 plus 3i equals to pi over 4. Okay, then you need to show that only one complex number that satisfies the both loci, then you need to label the point as P on your diagram. Okay, so which means in this case, so same thing, let's try to identify which type is the locus first. So we have modulus z is equal to 4, all right? So this will tell us that we have a locus of a circle for an, with a center of the origin, right, which is the 0, 0. So we also have a radius of 4. Okay, so by having this, then also we know that for the second one, the argument of z plus 2 plus 3i will be equal to pi over 4. Alright, so let's try to rewrite it in the form of z minus z1 also. So argument for z minus, so we have negative 2 minus 3i. Alright, then equal to pi over 4. So by looking at this, then you know that it's going to be a half line. So where is the starting point? Is going to be at negative 2 and negative 3i. Or you can write negative 2, negative 3 lah, okay, at an angle of pi over 4. So which means that the first thing we have is a circle first. So the center is at 0, 0 and the radius is 4. Then after that, you can try to draw the circle that you have. After that, the second one, starting from the point at negative 2, negative 3i. So which means negative 2, negative 3i is here. Yeah, then you can draw what is that called? A dotted line that is parallel to the positive real axis direction, right? So this is the reference line. So which means here to here is going to be pi over 4. Okay, so then you can draw a line. So it's like an infinite line. So that's why we will try to put an arrow at the back there. Okay, so show that there's only one complex number that satisfies both loci. So which means they will only intersect at one point. So which means it's true when we try to look at the diagram here. So which means this will be the intersection lah. So let's try to label it as P. Okay, so just like that. Alright, so let's try to look at number 7. Okay, 7, sketch on an Argand diagram the locus of the complex number z where z satisfy the equation for argument of z plus 2 minus I equals to 2 pi over 3. Okay, so same thing, let's try to identify what is the locus here. So we might need to rewrite it a bit. So it will become argument of z minus then 2 plus I. Okay, then equal to 2 pi over 3. So by having this, then we know that it's going to be a half line. that starting at the point of, or the complex number of 2 plus 1, then at an angle of 2 pi over 3. Okay, so after we have this, then now we can try to sketch it. So which means that you will need to have a point. So 2 and then, sorry, it's going to be -2, right? So plus, yeah, I'm sorry here, -2 plus I. So that's why it's -2 and then 1 here. Then with the reference line that parallel to the direction of a positive real axis. Then after that, we have the line. So from here to here, is going to be 2 pi over 3. Okay, so that's the idea. Okay, then now let's move on to B. So on the same diagram, shade the region whose point represent that the complex number z which satisfy this inequality here. Okay, so you can see that this is what that we have drawn, right? Because this argument has to be lesser than 2 pi over 3. So that's why it's going to be like the right hand side over here. Then after that, it's going to be more than pi over 2. So pi over 2 in degree, then it will be 90 degrees. So we know that if, let's say, we try to draw the other line, then it will be at the line here. Okay, so this is the 90-degree one, so which is pi over 2. Then after that, from here to here is our 2 pi over 3. Alright, so by having this, we know that the argument should be more than pi over 2 and less than 2 pi over 3. So that's why the shaded region will be everywhere in between here. Okay, so that's your shaded region. Alright, so Z, then you can just write down that Z may lie anywhere in the shaded region. Okay, or on the boundary. So on the boundary, which means that you also accept pi over 2 and also 2 pi over 3 lah, because it's more than and equal to and less than and equal to, right? So that's why your answer will be everything. Okay, so now let's try to look at the last question. Okay, number 8a, on the sketch of an argand diagram, shade the region whose point represent the complex number of z which satisfy the inequality of z plus 4 minus 4 times square root 3i lesser than 4. Okay, so by rewriting this, then we can get z minus -4 plus 4 times square root 3i is lesser than 4. Okay, so this is in the form of z minus z1 lesser than r. So this will form a circle, a locus of circle with the center of -4 plus 4 square root 3i and the radius is 4. Okay, so now we can try to plot, we can try to sketch our locus here. So 94, when you can straight away try to press in your calculator, like 4 times square root 3 is like 6.928. So in this picture, we can try to sketch it as 7 lah. So yeah, because 6.9 is like pretty near to 7. So it means -4 and then 7, so it's like roughly here. Okay, so this will be like our center. So you try to plot it as C. Okay, so now we move on for B. Find the least value of the modulus Z in this region. Okay, so by looking at this, so the modulus of Z, so now we need to understand that Z is the general point that on this locus, right? So if you want to find the least value for the modulus of Z, meaning that you are finding what is the least value when you try to find the magnitude of the position vector for Z. So that's why it will always come up from the origin here. Okay, so where do you think that it will be the nearest? So it will obviously to be at this point so that you can form a shortest line over here, so you can get the modulus or like the length of Z is the least in this case. Okay, so the problem here is how can we find this line? Okay, so let's try to denote the point here is like P. Okay, so this is O, then this is P. So now any idea can we try to do that? So we have the radius, right? Then can we find the distance of OC? We can do that, right? Because we actually have the uh coordinate for C, which is 94 and also 4 square root 3. So we can find what is our distance or what is the modulus for OC first. Okay, so modulus, this is B. So modulus OC is equal to the modulus of our complex number here, which is 94 plus 4 square root 3i, right? So now we can try to find what is the length. So 4 square and then plus 4 square root 3 square. Okay, so by solving this, then we can get 16, and then 4 is 16 times 3, so that's why 48. So this will give us square root 64, which we know that the distance of OC is going to be 8. Okay, so if OC is 8, then how can we find here? So which means that when we try to use our 8 to minus off the radius, then we will be able to find OP. Okay, so that's the idea. So OP will be equal to our OP is equal to OC minus our CP, which is the radius. Okay, so for the radius in this case, we know that it's 4, so that's why 8 minus 4. So from here, we know that the least value of modulus Z is going to be 4. Okay, so I hope that you can get the idea of it. Yeah, so basically it's that because this is like a sketch, then obviously then maybe our P can be here, can be anywhere. So as long as we know that the least will certainly happen somewhere here. But for us to find the exact point, right, we cannot actually know what is the coordinate, right? But for the length, then we'll be able to find it like for when you try to connect to AC, then you minus off the radius that we have here, then you can find the shortest distance over here lah. Okay, so for C, for part 2, so find the greatest value for the argument Z in this region. Okay, so I'm going to do it in another color so you can see like the difference here. Okay, so for B2, this is B1. Okay, so now same thing. You when you want to find the argument Z, right? So which means that your Z is a point that create the largest angle between the positive real axis and also your vector of Z. So which means that it will be somewhere over here because as we try to connect it to our O here, so what happens? So this will create the largest argument as it possible. Okay, so yeah, I hope that you can get the idea like what is that happen there. Okay, so I mean obviously it can be here, it can be anywhere, but we know that it's going to be like in this direction lah. Because if let's say the Z happened here, then you will have an argument that is lesser than this, right? So that's why we can try to denote it as A here. Okay, so how can we actually find the angle here? Then which means that perhaps we might need to find out what is the angle. Either the first choice that you have is to find out what is the coordinate for this. Then after that, you can find out what is the angle here. Then you use pi to minus it. But it will be difficult for us to actually find the coordinate here, right? So another alternative we can have here is, since this is the center, so I can always connect my center to this point. So this will create a tangent, right? Okay, then the same thing when I try to connect it from here to here. So this is going to be another line and this is going to be another line, and A is going to form another tangent, so which when I try to have the radius and the tangent, it will form another 90 degree over here. So by using the properties of tangent or like the circle that we learned before, right? So as long as we have the two tangent, they can intersect each other at one point, it will create two similar triangle. So that's why the angle here and the angle here is going to be the same, and then the angle here and the angle here is going to be the same. So if let's say I can try to find one of it, then I will be able to use pi over 2, then I plus the that plus the beta and plus another beta here. Okay, so how can we find this? Then the easiest one is by using this triangle. So we know that the distance from here to here is 4 and the distance from here to here is 4 then square root 3, right? So if we want to find the theta here, which means in this case, then maybe we try to denote this as b. Okay, so the angle that beta that we want to find is actually the angle for COB. Okay, so that's why we have the opposite and we have the adjacent, so we can use tangent to help us to find our answer. So tangent COB will be equal to the opposite is 4 and the adjacent is 4 then square root 3. So by solving this, then we'll be able to get the angle for COB will be equal to pi over 6. Okay, so now we have this, then now we can find the greatest value for the argument z already. So greatest value of argument z, okay, is going to be pi over 2. Okay, so which means here to here is 90 degree. Then plus we have pi over 6 and then plus another pi over 6. So beta and beta. Okay, so by solving this, then we'll be able to get 5 pi over 6. All right, so you have another alternative here as well. If let's say you want to find AOC also can. So if you are using AOC, right, so which is the two line that you already have the distance, so you also have the radius of 4 here. Then after that, by using what you get in B, right, you also know that the length for OC is 8. So that's why to find this, then you have your opposite and adjacent. So which means if let's say you try to use sine for AOC will be equal to the opposite, which is 4, then over the hypotenuse, which is 8, then you'll be able to get the exact same answer as well. Okay, so you can just try it out by yourself. All right, so yeah, that's the idea. So I hope that you can understand. So please spend some time to finish your homework. Then if you got any question, please ask me personally. So that's it for the last lesson here. Thank you.